Hi everyone, so good evening, welcome you all to the session. I hope I'm audible to all of you. Please confirm me in the chat if I'm audible to all. So good evening and welcome you all to the session. Folks, if I'm audible to all of you. Thank you for the confirmation and good evening and welcome again. Okay, so let's go ahead and begin with the session today, right? And so this is the day 2 of the workshop that we had started up in the yesterday, right? So we started up yesterday, and today we are on the day 2 part, which is where we're going to be completing this project which we started yesterday. So the set of topics that we've covered so far in the previous day's session, that includes the idea of right, so that includes starting from. So we kind of start up with the idea of understanding, well, this is a data science workshop and for who I am. And yeah, so we're going to start, we understood a little bit of overview understanding of what is exactly data science, right? So let me start with the recording, I'm sorry, right? So let me welcome you again, right? Just a second. Yeah, so let me welcome you again. So welcome you all again to the data science workshop. And we discussed today who am I, and we start with the idea of what is data science, right? So this is day 2 of the workshop on data science. We discussed all the idea of programming languages, and mainly we spent a lot of time, good time on understanding the journey of enterprise, what should be an ideal journey of enterprise with data science. We started to discuss about the project that we're going to work with, which is more of an analytics project. And that's where we talked about the idea of why machines are damaged, right? So this is a project that we work with. And so we have data set of, as you can see that we have a data set of around 1,000 machines with 7 columns. For each machine, we have lifetime, broken, pressure, moisture, temperature, team, and provider, right? So these are the attributes that we have. And broken column simply shows that whether this machine is not damaged or damaged or not damaged or damaged or not damaged, so on and so forth. And the objective here is to use this data, perform analytics using statistics and using data visualization to interpret why machines are damaged, right? So we have to answer the question, why specifically machines are getting damaged, right? So the factory administration observed that there are a lot of machines which are getting damaged, and you help them understand what's the possible reason behind that, right? So this is where we sort of discussed about the idea of blueprint of any data analytics project. How should it look like, and how should you approach what should be a step-by-step approach while working with any such problem where you have to answer this question, why it happened in past, right? So what should be a possible approach that you want to possibly take on the top, right? So that could be, this is the 5-step approach, which includes starting from domain exploration, which is where you want to spend time understanding the business domain, understanding how exactly the business functions, and identifying the possible business beliefs and the reasons as well, why those beliefs are there, right? Then second step, you want to work on data collection inside the business and sometimes outside the business as well. And you'd want to explore data, identify some common challenges with data. Third step is data cleaning, which is where you want to do the cleaning of data to handle maybe the duplicate entries, handle missing values or outliers as well. And the fourth step is a step where you actually perform the real analytics, which is what we're going to be starting up today. So we have seen already, so we started with here, we sort of loaded the data, right? So let me run this again. Right, so we have started with data exploration. We have seen df of head. We don't have any identifier. Info helped us understand that there are 2 columns which are having some categorical features like team and provider. And data has some missing values. We could observe here that data seems to have some missing value, right? So this is what our analysis was. We then further looked into the unique values of team and provider, identified that what are the unique values or categories that it has. We also identified that as the data I mentioned was object, it doesn't contain any string, which might represent a missing value. We looked at the df.describe to look at the statistical summary. We identified that, well, here it looks like there's a huge difference in 75 percentile and the maximum value of the right? And that's where you can say this huge difference shows that this huge difference shows that the data has some outliers possibly, right? This particular column moisture has some outliers. Right, then we talked about the data cleaning part, right, which is where we start with, which is where we take multiple steps. First is like checking for duplicate entries, right? So df.duplicated.sum is helping us out to identify that how many rows are duplicate. We identified 0 rows. We checked for missing values. We found that, well, pressure has 4 missing values and temperature has 3 missing values, right? So these are the missing values in the data. Uh, so in order to handle the missing values, we looked at that if the data is categorical, if it is nominal, you would want to fill the missing values by mode. If it is ordinal, you would want to fill it by median, right? And for numeric, accordingly, we have different situations. Right, we looked at the skewness of data. We understood the concept of skewness as well, right? And scaling of data as well. Outlier, we identified that there is an outlier that we have, and uh, we try to clean that as well, right? So this is what you've seen so far. I'll just take a moment, pause, just to give me a minute, everyone. Okay, so yeah, this is what we have seen so far, right? And we're going to be sort of looking further on the top of this, and we're going to be starting with the EDA part, which is exploratory data analytics, right? So give me a moment, and let's start with this. I'm sorry for the inconvenience. Like, looks like there was some issue with the internet with me. So I hope I'm audible now. Am I audible now to all? Can you all hear me? Please confirm me in the chat.
Yes, sir.
Thanks for the confirmation. Apologies for the inconvenience. And let's get started, right? So yes, we're going to be now starting with the idea of EDA, that is exploratory data analytics. As we already discussed that, what you do in EDA is like there are two methods to perform EDA, which include the idea of EDA with data visualization, and the other is EDA with statistics, right? So these are the two primarily methods to implement EDA, which is like exploratory data analytics. Right, so we're going to be implementing these two things, right? And this is what we're going to be doing in this data set. So first, we're going to be starting with the idea of EDA with data visualization, right? So this is what we're going to be starting with. EDA with data visualization. And so in that, as we can see that there are three methods primarily, which is like univariate analytics, bivariate analytics, and multivariate analytics. Now, what exactly is univariate? Univariate is where you analyze one attribute at a time. And bivariate is where you analyze impact of one attribute on the other. Multivariate is where we analyze impact of multiple attributes on the target. So in univariate, we don't look at the role of that why machines are damaged, right? So we don't look at the impact on the target attribute, right? So if you look at the columns that we have in our data, right? So if you look at df.columns, these are the columns. Broken is the column which is our target attribute or our KPI, right? So we want to identify that why machines are broken, why machines are damaged in general, right? So in univariate analysis, we don't compare with the sense that why machines are damaged. We do that in bivariate and multivariate, right? So let's start with univariate first. In univariate, we'll simply look at the idea of what information does a particular attribute, represents, or what information does it have, right? So that sort of stuff we look at in case of univariate analytics. And yeah, so that's what we do here in general, right? And so let's start with that, right? So we can look at, there are two types of attribute, as you already know, for categorical and numerical. So whenever you have to plot a graph, what graph to use? So generally for numeric, we should use always histogram to represent, and for categorical, we use bar plot to represent the information, right? So these are the two things that we do, histogram versus bar plot. Right now, yeah. So this is one general understanding of what kind of graph can be used for univariate analytics. So all of this data, if you look at again, df.head here. So all of this data, as you can see that for categorical, broken, team, and provider are categorical attributes. Rest all are numeric attributes. So let's do it for categorical. So we can say cat. I would request all the themselves if you don't have any question, right? So please keep your microphone on mute in case you do not have any question. So yeah, coming back here. So well, first let's say do analysis of categorical, which is, as we know, that broken, team, and provider are the categorical attributes, right? So like rest, the pressure, temperature are more of numeric attributes, right? These are three categorical. So we can simply say that for column cats, that means for each of the column, we can do pld.figure fixed size equals, let's say maybe 8 by 6, right? 8 by 4. SNS dot, we can do count plot, right? So count plot is a way to draw a bar plot, right? So that's what we're doing here, and pld.show. So this is going to just draw a count plot of 3 columns, which is broken, team, and provider, right? And this is where we're going to be starting with the analytics. So let's start with that. First, broken, right? This is one of the categorical attribute, which represents simply the machines are damaged or not damaged. So count plot is primarily a frequency plot, right? So x-axis represents the categories, and the y-axis represent count of how many times those categories are being observed. So out of 1,000 machines, 600 machine approximately are 0. That means they are not damaged. And approx 400 machines are 1, which is damaged, right? So y-axis shows the count. So 1,600 are not damaged and 400 are approximately damaged. That means almost 40% of machines are damaged in the factory. right? That's one of the interpretation we can make here. Here we can see that the teams, right? So that means this graph simply represents how many machines are managed by team A, team B, and team C. X-axis represents categories, which is like team A, team C, team B, right? It is not in proper order. It should have been team A, B, C, right? Because it picked up the order based on the occurrence of the values in the column, right? So maybe the first machine would have been of team A, second of team C, and maybe third or eighth of machine would be team B, like that. So team A, as you can see that almost somewhere around 330 machines are handled by team A, close to 300 are handled by team C, and close to 350 are handled by team B. So team C handles a little less of machines, and approximately all the teams are handling, in general, uniform number of machines. You can see that, approximately they are equal, right? So the count of machines managed by or handled by team A, B, C are almost equal. Each team is provided almost equal number of machines to manage. Similarly, when you look at provider, so this is simply univariate analysis, right? So this is the code that we have done so far, right? This is simply univariate analysis, which is where we are simply analyzing the impact of an attribute on a target. Impact of the analysis of an attribute without looking at the reference with target, right? So we are not looking at the reference with target. So, provider simply shows that there are 4 providers, provider 1, provider 2, provider 3, provider 4. And the number of machines purchased from each provider, each vendor is approximately equal as well. It's just provider 2 has a little higher number of machines being delivered, and provider 3 and 4 lesser, provider 1 is a little higher, like that, right? So there's a frequency of the machines that they're delivering, to the factory. The count of machines that they're delivering to the factory. So this is simply univariate. So we look at only provider. We are not looking at that how provider is impacting damaged or not damaged, how team is impacting. We are not looking at that at the moment. This is very simple univariate analysis. So we simply look at one of the attribute and try to make sense out of that. What kind of information does it represent? So as you can see, that broken shows that almost 40% of machines are damaged. Team shows that team B is handling a little higher number of machines compared to A and C. Provider shows that almost all the providers are providing or selling out almost equal number of machines to the factory, right? So it's being equally, equal prioritized, the vendors or sellers are. So are we good with this? If you're good, right? So we can write here analytics, which could be almost 40% of machines are damaged or broken, you can say, right? So they are damaged or broken. We can say that almost all teams are handling or managing equal number of machines. All the machines are, you can say, purchased from vendors, provider 1, 2, 3, 4, or you can say that the frequency or the count of machines purchased from each provider is uniform. That means it is almost equal, right? So these are the few analytic steps that we analyze here, right? These are the few analytics that we identify here. Let me know if this makes sense, everyone, if you're good with this. I hope this makes sense. Let me know if you're good with this. Okay. So this is some simple univariate analytics for categorical attribute, right? As you already know that for categorical, we should go for bar plot. And for numeric, which we have not done so far for few of the columns like lifetime, temperature, pressure, moisture, which are numeric, right? So for them, we should always go for histogram. Right. So similarly, now we'll go for numeric attributes, right? And we'll try to perform the similar analytics on the numeric attributes. right? So you can see that numeric, okay, which is lifetime, broken, pressure, moisture, temperature, so on and so forth, right? So these are the attributes that we have, and yeah, these are the attributes that we have here, right? So out of them, broken is not numeric, as we already know that it's categorical. So we would want to do similar analytics for numeric attributes, which is where we would want to possibly draw a histogram plot. Right, so PLT dot hist, we can say df of call, PLT dot show. We can put a title as well, PLT dot title of call. So these are the columns which we are looking at, right? And so now if you look at numeric, first graph is lifetime. As we can see that from lifetime, for the value of lifetime up to 60 months, right? So the lifetime is in months. How many months a machine is older, you can say, right? So when it comes to months, approximately up to 60 months, the number of machines are uniform, but more than 60, they are huge number of machines. More than 80, they are very high number of machines, right? So maybe these are the oldest machines so far, right? You can say that those which are more than 80 are the oldest machines, and possibly these machines would have been purchased when the factory would have started somewhere around 80 or 90 months back, which could be, let's say, around 7 years, around 6 to 7 years back, right? So when 6 to 7 years back, the factory would have been set up, right? At that moment, possibly they would have purchased higher number of machines. And then there was maybe for around a year or 6 months, they didn't purchase much of machines, but then again, they purchased higher number of machines, and then the uniform number of machines are being purchased almost every month, right? So the sort of lifetime of, the machines is uniformly distributed up to 60 months, and then it has a little peak, and then again, another peak that we have in the data distribution. So this is simply, it shows, and you can see that it's almost ranging between 0 to somewhere around 90, right? 0 to 90, it's ranging between approximately, right? And that's how the data is distributed. It is uniformly distributed from 0 to 60. If you look at now pressure, it's almost a normal distribution, as we can see. Almost normal distribution for pressure, not skewed. For example, for lifetime, is it a normal distribution or skewed distribution? Excuse me. Is it a normal distribution?
Skewed, sir.
So I hope all of you agree that this is more of a skewed distribution, right? And when you look at similarly, right? So this is skewed distribution. That means there are a lot of machines which are pretty much older because they have very high value of lifetime, right? And there are few machines which are like very new, you can say. Pressure is almost a normal distribution, as we can see that, right? It's ranging between 40 to 160, but most of the machines are operated between the value of pressure 80 to 120. So that's a standard popular range within which the machines are being operated, right? Moisture, as we can see, moisture is like very much skewed distribution, right? It's super skewed distribution actually, right? So why is that? That's a little challenge with it, right? So moisture, we haven't we cleaned moisture, right? So might have to check it that. Maybe I didn't clean the moisture part. I didn't run this cell possibly, and even this one as well, which is where we are dropping the missing values. Yeah. So pressure, and then if you go to moisture now, so now it is almost a good distribution. So still moisture, as you can see, that moisture is not a normal distribution. It is a skewed distribution. Most of the machines are between 80 to 120, but then there are few machines which are being operated on a little higher temperature. Moisture, which is like 120, 180 to 200. These machines are generating high moisture. So mostly it may be possible those machines which generate high moisture might be getting corroded and possibly they might be getting damaged. Could be a possibility, right? We are just looking at a possibility. But we can see that, a majority of the machines are generating less moisture, but then there are a few exceptional cases which are generating more moisture, right? So generating more moisture might be leading to corrosion, right? And corrosion might be leading to damage or breaking of machines, possibly, right? So we can make some conclusions on the top of this, right? That's one of the things, right? And so you can see that, most of the machines are having between 80 to 120. So it could be a possibility that 80 to 120 could be a possibly safe range of moisture. We are not sure with that because this is univariate. Temperature is almost a normal distribution, right? So it's almost a normal distribution. Most of the values, machines are operating between the temperature 80 to let's say 120, right? So we can write our analytics here. Lifetime is skewed distribution. There are few machines having exceptionally lower value, right? So it's more of positively, negatively skewed of lifetime. Then it was pressure. Pressure is normally distributed. Most of machines are operated with pressure between 80 to 120. Then temperature is skewed. Sorry, temperature is normal distribution. Right, and most of machines are operated with temperature between, here also you can say almost around 80 to 120 or maybe 70 to 130. Finally, moisture. Moisture is skewed distribution. And there are few machines which are generating exceptionally higher moisture, right? So these are the few analytics that we identify from our data from the graph, right? And so this is what we do in univariate analytics. In univariate analytics, we don't look at the impact of one attribute on the other, but rather we just analyze the overall idea of one attribute, right? And we collect some doubts, right? So we try to always collect some doubts which we would want to possibly verify in the bivariate or multivariate analytics, right? So let me know if this code makes sense, everyone. Are we all good with this? Any questions if you have, let me know that as well. We're good. Right, so let's move further. Right, so now we're going to be shifting to the idea of bivariate analysis. Right, we're going to be shifting to the idea of bivariate analysis. Yeah, one of the way to look at whether the data is normal distributed or it is skew distribution is look at the skewness. And the other way is look at the, so you can technically look at this value of skewness and based on that you can judge whether it is normal distribution or it is a skewed distribution. The other way is like, by looking at the graph, if it is symmetric on both the sides, as we can see that, both the sides of 100, it is almost symmetric graph for temperature. So it is normal distribution, right? Whereas here you can say alongside the median, which is the central value, let's say 130, alongside 130 central value, it is not symmetric, so it is a skewed distribution, right? Moisture, it is symmetric alongside the central value, so it is skewed distribution. Sorry, it is normal distribution. Here it is not symmetric on both the side of central value, so it is skewed. Other ways to always look at the skewness of the value. So when you do df dot skew, that also shows whether data is skewed or not. So you can see that here. This simply shows whether the data is skewed or it is normal distribution. And so you can see that this is almost closer to lesser than 0.1. This is also almost close to 0.1. So both are normal distribution. Whereas this is a skewed distribution, less than minus 0.1, right? And this is this is also skewed distribution, more than plus 0.1. So both are the ways. One is like look at the value of skewness, and second is the graph as well that shows it. So now we're going to be shifting to the idea of bivariate analysis, and this is where we're going to be looking at the idea of how do you assess how a particular factor is impacting the other factor, right? And this is going to be interesting. So here we go. So in bivariate, you may want to compare two attributes together, right? So which is where you can say you may want to compare a numeric versus a categorical. The other one could be you would want to compare a categorical, as our target is categorical, versus categorical, right? And the other one could be you want to compare numeric versus numeric. We don't have a situation of numeric versus numeric, so we'll not be looking at that. But yeah, we'll be looking at what graphs to use. Yeah, so Abhijit, so that's what those kind of things we do in bivariate or multivariate analysis, right? So there are multiple options of what kind of graphs can we draw and what are the functionalities available, right? But we do that in multivariate analysis or bivariate analytics, right? So pair plot is a part of multivariate analytics where you look at the impact of multiple attributes on multiple attributes and you do altogether analysis, right? So yes, pair plot does works, but it is part of multivariate. Right. In univariate, you would want to always check one variable at a time. Right. So whenever you have to compare a numeric versus categorical, one of the way to look at is probability distribution of data, probability distribution of data, and we all simply call it test plot actually. Whenever you want to compare categorical versus categorical, one of the way you can do it is bar plots. Comparison numeric versus numeric, you can actually do here a scatter plot comparison. Right? So these are the multiple options available. So now let's say that we're going to do similar analytics. So first we're going to go for numeric versus categorical. As part of that, we're going to impact, let's say, lifetime versus broken, right? So broken is categorical, lifetime is numeric. So we can simply say plt dot figure fixed size equals, let's say, 12 by 5, possibly, right? So that is the width of the graph and 5 is the height of the graph. We can say sns dot dist plot, right? Which is like df of lifetime, or we can simply say df dot lifetime, where df dot broken, right? So df dot broken equal 0, right? So we are drawing the graph of lifetime where the machines are not broken, right? And we can mention this as let's say let it take the default color. And the other is, so this is for machines which are not broken. So we're trying to draw a distribution plot of the lifetime of the machines which are not broken. If I simply do plt.show, so this graph at the moment simply represents the distribution of lifetime of the machines, right? So the lifetime value of the machines for those machines which are not broken, right? So it's representing the data of those machines which are not broken. So you can see that x-axis represents the lifetime and y-axis represents the probability distribution, right? Which is like the percentage of machines existing which are not broken at that particular value, right? But in case you want to make sense of this, it's better to compare this probability distribution with another probability distribution of the machines which are actually broken for the legend, so that we can simply see what are the values which graph represents, right? So we have now two distribution plots, everyone. The red distribution and the blue distribution, right? So the red and blue, you can call it orange and blue. As you can see that blue is representing 0, right? So broken 0. That means 0. 0 simply represents, you can say, not broken. And 1 means yes, broken. Right? So 0 means not broken. That means blue distribution is representing the probability distribution of machines which are not broken, not damaged. Red distribution is representing the probability distribution of machines which are damaged. Right? So there are two distributions. X-axis represents the lifetime of machine. Y-axis represents the probability of each distribution. And there are two distributions here which we are comparing, the blue distribution and the red distribution. Blue distribution is the distribution of machines which are not damaged, whereas red distribution is the distribution of machines which are damaged. Looking at this, what do you think a kind of pattern that present here? So what do you think that this kind of pattern could be a possibility here? Well, can we say that below 60, do we have any red distribution? So can we say that below 60, do we have any red distribution? Below 60, between 0 to 60, do we have red overlapping blue? No, right? Below 60, there is no red. There is a estimated line of red, which you can ignore, but there is no bar of red, right? So below 60, there are no machines which are damaged, right? So one of the pattern you can see that is below 60 months, there are no machines which are damaged. That means almost every machine is surviving up to 60 months, right? So the bar represents actual data, the line represents the approximate value, approximate distribution of value, right? So let's say that, generally the lifetime of machines cannot be negative, right? So the line here, you can say the blue line represents that, okay, if this is the data distribution, approximately, so this is more of, you can say, interpolation, approximately this could be the distribution here, right? So the line represents the approximate distribution based on the actual data, Okay. So mostly you can make sense of these bars, right? So these bars are important, right? So what do you think here, the pattern that is present? So can we say that almost every machine is surviving up to 60 months, right? Below 60, there is no red bar, right? That means there are no machines damaged below 60 months. That's one point. And after 60 months, the machines are starting to get damaged, right? After 60 months, also there are few machines which are surviving. It's not something that after 60 months, that means after 5 years, every machine is damaged. But yeah, after 5 years, the lifetime of machine is decreasing. The usability of machine is low, possibly, it looks like. And up to 5 years, the machines are surviving pretty well. Maybe after 5 years, few machines are capable of surviving, few machines are capable of surviving, and most of the machines are getting damaged. Right. A chunk of machines are getting damaged in possibly 60 to 70 months, and then another chunk of machines are getting damaged around 80 months, you can say. Right. So are we all good with the understanding of pattern? What pattern does exist here from this graph, everyone? Let me know. Right. So we can say that analytics that exists here is almost all machines are surviving up to 60 months, right? And so up to 60 months, they are not getting damaged. After 60 months, the machines are starting to get damaged, right? So after 60 months, the machines are starting to get damaged, right? This is one of the patterns that exist. So do you think lifetime is an important factor to identify if machines are going to be damaged or not? Is it lifetime an important factor? Do you agree with that? So I hope all of you agree that lifetime is an important factor, is definitely an important factor to estimate whether the machines are damaged or not damaged, right? So if lifetime of the machine is less than 5 years, it's very likely that machine is not damaged. If it is more than 5 years, there are chances that it will not damage, there are more chances that it will get damaged, right? As you can see, after 60 months, the probability of damage is quite higher compared to the probability of not damaged, right? So the line represents the probability plot, you can see that after 60 months, the blue is lower than red. Red is quite higher than blue. That means the probability of machines getting damaged is quite higher after 60 months compared to the machines not getting damaged. Are we good with this? Right. So I hope you are good. So similarly, we can look at another factor, right? So we can look at, let's say, possibly other factor. Instead of lifetime, let's say we want to look for temperature versus broken. So I just copied the code and replaced it by temperature. So now if you're looking at the analytics of temperature versus temperature versus broken, so we again have two distribution plots: the blue distribution and the red distribution. The blue distribution is for the machines which are not damaged. The red distribution is for machines which are damaged. Distribution of temperature attribute, right? So x-axis is representing temperature, and y-axis simply represents the probability of machines damaged or not damaged at that value of temperature. So can we say that, well, here in this graph, can we say that the blue distribution and the red distribution is almost overlapping each other? Do you agree with that fact? That the blue distribution and red distribution is almost overlapping each other at every point? Right? I hope all of you agree with that. That means at every value of temperature, the probability of machines getting damaged is almost equal to the probability of machines not getting damaged. That means as both the distribution plots are overlapping each other, that means at each of the value of temperature, the probability of the machines getting damaged is equal to the probability of machines not getting damaged. So can we say that way temperature is an impacting factor or not? What do you think? Do you think temperature has some information to say why machines are damaged or not? So I hope all of you agree that temperature has no information to say why machines are damaged. Right? Temperature has no information to say, right? It cannot give us any idea about why machines are damaged. Lifetime could give us idea that those machines which are less than 5 years, they are not damaged, right? But more than 5 years are damaged like that. But we don't get any such information from temperature, right? So temperature is not having any such information about why machines are damaged or not damaged like that. So the number of machines which are damaged or not damaged at each value of temperature is equal like that, right? So it is not an impacting factor. I hope you're good. If you have any question, feel free to put that, everyone. Okay, so here we go. Let's compare this with now, instead of temperature, possibly moisture. So now we have again two distribution plots, this time for moisture attribute, right? The red distribution shows the machines which are damaged. The blue distribution shows the distribution of moisture for the machines which are not damaged. So is it that the two distribution plots are completely overlapping each other? The blue and red are completely overlapping each other? No, right? X-axis represents here moisture and y-axis represents probability of machines getting damaged or not damaged according to red or blue. As we can see that between the moisture of 75 to 125, which seems to be good range, the probability of blue is higher than red. That means between 75 to 125, most of the machines are not damaged. But when the machines are producing moisture more than 125, that is where machines are almost all damaged. Right? As you can see, above higher than 125, there is only red distribution, there is no blue distribution. That means machines which are generating moisture more than 125 are all getting damaged. So possibly if they are generating more moisture, they're getting corroded and they're getting damaged. Could be a possibility. We don't know that, but yeah, that's what data says, right? So what data says is that between 75 to 125, the machines which are producing moisture between 75 to 125 are less likely to get damaged. But if they are producing moisture more than 125, they are more likely to get damaged. Right. Are we all good so far? Good. Right. So moisture seems to be an impacting factor. I hope all of you agree on that point. Right, so moisture seems to be an impacting factor and seems to be an important attribute to say why machines are getting damaged. Okay, so here we go. Next, we're going to be going with another last attribute of numeric, which is, let's say, pressure. Right, so pressure. So we've got the graph for pressure, and we can see that for pressure also, almost at every value of pressure, so we have two distribution here as well, the red distribution and the blue distribution. The red distribution is almost overlapping the blue distribution. So we can say that, at every value of pressure, the probability of machines getting damaged is almost equal to the probability of machines not getting damaged, right? So that's where you can say that, both the probabilities are almost equal to each other, right? So that way, I hope all of you agree that possibly pressure also doesn't seem to have some information to say why machines are getting damaged, right? Pressure also doesn't seem to have any information to say why machines are getting damaged, right? So that's also another important information that we get from this. All right, I hope we're good. So this is more of bivariate for numeric versus categorical. We are here to check out the idea of categorical versus categorical as well, right? So this was more of an idea about numeric versus categorical, right? So like that we can do for almost every attribute. Next, let's say that we want to do it for categorical versus categorical, right? So categorical versus categorical, that's what you want to do here. And yeah, so that's what we know. You can say more of extract information here. So let's say that I want to compare maybe team versus broken, right? So we have team as a categorical attribute. So we want to analyze that how teams are impacting the machines which are damaged or which are not damaged possibly, right? So that's one of the analysis we want to see. So well, we can use a graph called as bar plot, right? That's one of the way to consume that. The other way to consume, which is where we kind of can use a method called count plot, right? that can help us integrate this, right? So let's say we can first draw the PLD.figure, fixed size equals 6/3, SNS.count plot, and we can say SNS.count plot df of let's say team, and PLD.show. So this is the we have not put any filter about broken or not broken. This is the plot of all the teams, how many machines they are operating for team A, B, and C, like that. And y-axis shows the count. And let's compare this with possibly the machines, being operated by each team, and the machines are damaged, right? So we're going to say that df.broken is equal to 1, right? So the machines are damaged. So now we have two graphs. The first graph shows the total machines operated by team ABC. Second graph shows the machines which are damaged operated by team ABC. But the order is not same. So maybe you want to change the order here, right? So we want to change the order here. So you can say order equals df dot team dot unique. So now we have in the same order, you can say, right? And so team A, team B, and team C, like that. So the first graph shows the total machines being handled by team ABC. And the second graph shows the machines which are damaged and are being handled by team ABC. The pattern almost looks similar, right? There is no huge difference, or there is not much of difference, as you can see here. It looks like that team A has slightly less number of machines which are damaged, right? So when it comes to total machine, team A is higher than team C, but when it comes to damaged machine, team A is equal to team C, you can say, right? When it comes to total machines, team A is higher than team C, but when it comes to damaged machine, team A is equal to team C. So possibly team A is damaging lesser number of machines. Maybe you want to check out the actual values over here. For that, we can also do here, let's say out equals 3d dot cross tab df dot team, comma df dot broken, comma margins equals true. Right, so this is what we have, and it simply shows here that the idea of the number of machines which are damaged, not operated by team A, and operated by team A, and the machines which are not damaged, operated by team A. Similarly for team B and similarly for team C. To look at the probability or percentage, we can simply say team of out of 1 divided by out of all. Right? So to look at the percentage of damaged machines by team ABC, as you can see that for team A, the damage percentage is least, which is a little higher for team B and team C. That means the way team A is managing the machines is a little better compared to the kind of care team B and team C takes, but there's no huge difference, as we can also see that, the difference, the overall damage rate is 39%. Team A's damage rate is 36%, which is lesser than the overall average, but team B and team C are having value higher than the overall average. That means team A is taking care of machines much better, or maybe they are handling machines much better compared to the way team B or team C is handling the machines. They are group of workers, you can say, right? In the factory, they are group of workers. They are different teams. Here's a widget. So team A is, let's say, a group of 80 workers, and team B is a group of 80 workers, and similarly C is a group of 80 workers, like that. So they are sort of a contractual workers or under a common contractor, like that. So team A is a different contractor, team B is a different contractor, team C is a different contractor. Right, so the way it looks like, the way team A is handling the machines, it looks like they are handling the machines a little better way. They have a little lesser damage rate. So, but there is no very huge significant impact, we can say, specifically when it comes to team. Maybe we can have a little different impact, or maybe we can have some impact when we look at multivariate analytics, combine team versus lifetime versus team versus lifetime versus damaged. Possibly, if we combine that, we may see, or we may identify more, much better interpretation, or maybe much better graphs. Okay, so that's one of the things. That's one of the things for here. Next is, let's say that you want to do similar stuff for provider versus broken. So we can again do the similar way. You can say we can kind of draw the similar graph, or maybe we can also do cross tabbing like this, and look at the percentage. So here we have the percentage of machines which are damaged and they are produced or sold by provider 1, provider 2, provider 3, provider 4. As you know, that overall damage rate is 39%, which is like almost 40%. But the machines provided by provider 1 are damaged. 45% of machines provided by provider 1 are damaged. 34% of machines provided by provider 2 are damaged. 47% of machines provided by provider 3 are damaged. And 31.9, which is like 32% of machines provided by provider 4 are damaged. Right. So this is a percentage of machines which are damaged, by different providers. So it looks that they are different, a little different in terms of variation and maybe the range. So the percentage of machines provided by 3 providers, which is like provider 1 or 3, are highly getting damaged, whereas the percentage of machines which are provided by provider 2 and 4 are lesser getting damaged. Possibly, they are more qualitative machines, you can say, which are manufactured by specific providers or manufacturers. Right. So maybe this may have some information, that could be an agreed point, you can say, right? But it's not very clear. Maybe we can get it more clear once we look at multivariate analytics and combine this with some numeric attributes as well. So graphs makes it more sensible to look at the logic and interpret what and why and how is it happening in the data. Statistics simply shows you what. It gives you answer to the what idea, which is like what happened in the data. No, sum should not be 1, right? So sum should not be 1, right? So this is the percentage out of the total machines. So the sum of machines which are damaged and not damaged, right? So that should be 1. So for example, if I look at the same thing here, out of 0 by all, so you can say that sum of this and this should be 1. Sum of this damaged from provider 2 and not damaged from provider 2 should be 1. Damaged from provider 3 and not damaged from provider 3 should be 1, like that. Okay. The meaning of categorical, that means that particular variable has categorical attributes like, team A, team B, team C. So there are 2 types of variables in 3, numeric versus categorical. Numeric means the values are mathematically higher or lower than each other. Categorical means values do not have mathematical relationship. Like in team case, team A, B, C are categorical because team A is not 12 or 30 higher than team B. Team B is not X, Y higher than team C. They don't have any mathematical relationship. Provider 1, provider 2, manufacturer 1, manufacturer 2, 3, 4 do not have any mathematical relationship. But in case of temperature, multiple values do have mathematical relationship like that. So broken is like 0 and 1. Yes damage, no damage. So yes and no doesn't have any mathematical relationship. Right? So broken simply shows 0, 1, yes, no, yes, no. So when it is like 0, 1, 0, 1, it is binary. When it is binary, it is categorical. Well, so that was the idea of bivariate analysis, everyone. Right? So that was the nutshell idea about bivariate analysis. Let's go for more. And now we want to dive deeper into multivariate analysis. Right? So we're going to look at the idea of multivariate analysis. Right, so here we go. And we'll look at the idea of nutshell idea of multivariate. So multivariate is like where you compare multiple attributes together. Right? So for example, let's say you want to compare a numeric versus categorical versus categorical. In such situation, we can make use of swarm plot, or maybe we can also use point plot as well. When you compare numeric versus numeric versus categorical, that's where you would want to use possibly scatter plot. Right. So let's look at both the situations and with one example each, and try to understand that how these comparison might help us, and what kind of pattern can we extract out of those. Right. So yeah, that's what we can look from this. So yeah, that's one of the analysis. That's sort of some simple analysis we can make out of this. Let's go ahead with that. Yeah, so here we go. So let's say first we're going to be talking about the first case, which could be this one. Maybe we can look at 2 examples of this case. Right. So let's say that we want to compare possibly lifetime versus team versus maybe broken. Right. So that's where we can say PLD.figure fixed size equals 12 by 5. SNS.swarm plot. X is categorical. So on X you had always pass a categorical, which is in our case going to be team. Y should be numeric, which in our case is going to be lifetime. U should be categorical, which in our case is going to be broken. And we have to mention data is df pld.show. So now we have here data, right? So we have here drawn the plot. Right, so we have drawn here the plot of the graph, right? So x-axis shows simply team A, team B, team C, and y-axis shows the lifetime. Now this is the swarm plot. So every dot here is a machine. So there are total 1,000 dots here. So x-axis is a team, y-axis is lifetime, and U is simply, the meaning of U is color, right? So color is like broken. So broken is represented by 2 different colors. 2 categories represented by 2 colors, 0, 1, which is 0 for blue and 1 for red. each dot is one machine. As we can see that the red dots, which are broken machines, blue dots, which are not broken machines, not damaged machines. So red dots are always starting from 60, right? So that means all the machines are at least surviving up to 60 months, which we also seen earlier as well in bivariate analysis. But then, what do you think? So do we have any particular team where the machines handled by that team are surviving lesser compared to the other teams? Right. So I hope you might agree there's a little difference of team C. As you can see that the machines which are, for team C are, all the machines are getting damaged a little early, right? Which is like slightly, right? So there's no huge difference, but yeah, there's a slight observation that you can make. The maximum level, you can see the maximum survival day months is a little lower for team C machines compared to the machines handled by team A and B. No much of other difference we can observe here. But that's not much viable business-wise, maybe not much, which is not worthy point you can say. Let's say that we want to do possibly a similar analysis of lifetime versus providers. Instead of team, let me make it a provider and do the similar plot. So, well, in case of provider, what do you think? What kind of pattern is present here? What do you think the kind of pattern is present here? Right. So I hope all of you agree that the machines which are produced by provider 3 are surviving lesser compared to the machines which are produced by other providers. Right. They are getting damaged early. Right. So almost all the machines which are getting damaged after 5 years are almost all of them are actually from provider 3. And for provider 1, 2, and 4 are surviving more than 5 years. Maybe they are surviving up to 6 years or at least. And so from 5 to 6, that peak was actually contributed because of possibly bad quality machines from provider 3. Whereas the most qualitative provider at the moment seems to be the provider 2. I hope all of you agree with that. Right. So these machines manufactured by provider 2 are surviving up to longer, and they are sort of getting damaged after a little very late stage, you can see. Right. Because of 3. Because of 3, provider 3, yeah. So you can say, yeah, that's one of the ideas. So this is what you do in multivariate analysis. We kind of compare multiple factors with the target, right? So which could be provider versus lifetime versus broken. That's what you're comparing here, right? So that's one of the analysis that we did here. So this was more of an idea about numeric versus categorical versus categorical. Let's say that now I'm going to shift to the idea of numeric versus. So I'm not writing the analytics, but that should be there. After every graph, you would want to write the analytics about what do you interpret from that. So let's say that I'm going to compare maybe lifetime versus moisture versus broken. Right. So we can do PLE.figure. Fig size equals 12 by 5. SNS dot scatter plot. X is lifetime. Y is moisture. Right, so it is. Yeah, you would be. You can now ask, as it's going to be completing today. So after today's session, you can kind of drop an email to our TechTrend website and then official email ID or your point of contact, and you can ask them and they'll send it to you. right? So I'll share it to my point of contact at different pinches. So it's not a challenge. You can always ask for the children on the party. So yes, this is lifetime versus moisture, that both numeric and hue we're going to be giving to broken, and we're drawing a scatter plot data, which is like is DF, right? And we'll show. Right, this is scatter plot we have everyone. So again, each dot is representing one machine, right? So each dot is representing one machine. X-axis is representing lifetime of the machines. Y-axis is representing the moisture of the machines, right? The moisture that machines are generating. And blue dots are the machines which are not damaged, and red dots are the machines which are damaged. So what do you think? What kind of patterns are present? And do we have any combined pattern of lifetime versus moisture over here in this data? Right. Do we have any combined directional impact from both of them? So as you can see that machines which are operated more than 60 months, irrespective of value of moisture, are getting damaged, right? So damage starts at 60 months, right? So machines which are operated for more than 60 months, irrespective of the moisture generated, are getting damaged. And then any other pattern with respect to moisture also you might find some. Right, so you might say that, well, when you look at the moisture, maybe the moisture more than 120 or maybe 130. So the value of machines which are producing moisture more than 120 or more 130 are almost all getting damaged. I hope all of you agree with that point. Right, so 120, 130 or 140 possibly. Right, so beyond that, almost all the machines are getting damaged. So higher moisture producing machines and older machines are more likely to get damaged. Then there are also some patterns available, which is like machines manufactured from a particular manufacturer, or slightly machines managed by a specific team also are having few challenges or issues with the quality, which is also leading to damage of machines. Right. Have a good next one. Okay, so that's the idea so far. This was the idea of multivariate analytics, right? So this is what we do as part of multivariate analytics in general, right? And so this was more of idea about how do we use data visualization. At the moment, it's more easier to interpret data visualization, right? Yeah, we can actually talk about pair plot as well. It simply shows again more of bivariate, right? So there's also one of the master plot. Everyone, we can also use more of like pair plot of DF, which kind of draws the graph of all the attributes versus all the attributes, right? So I forgot to mention really.show. That should be there on SSD, but yeah. So this is also kind of graph which gives, but the challenge with pair plot of Bivariate is that one, it shows a little smaller graphs, and you have to kind of look at each column versus each column, which becomes a little difficult in some situation. It doesn't show much of colors. If you want that to show with a specific attribute like broken, not broken, you want to show by red and blue, which is not by default there. But yeah, those options are, there are few options to customize this plot at the moment. But yeah, so there's one of the plot which gives kind of one short analysis of all the columns versus all. The only thing is it looks, look-wise it's attractive definitely, but when it comes to interpretation, it becomes a little difficult because of small size of the graph. It becomes a little difficult to make sense out of this. So similarly, there are a few more plots which you would want to explore, everyone, with Seaborn. Seaborn is a super powerful package in Python which has a lot of functionalities in terms of drawing different plots. with the data, right? And can be helpful in order to identify a few can be helpful to identify why machines are damaged or maybe such similar situations. So these are all methods which kind of can be used for with the help of data visualization. You can make sense out of these methods and use them for exploratory data analytics to identify why a particular event occurred in past. Right. So we got a few answers to the question why the machines got damaged. Right. So are we all good with that? Any questions we have, let me know. Okay, so now the next segment and last segment, which you're going to shift to the idea of a little bit understanding of what are the statistical methods that can be used for the situation. So possibly you would want to use the EDA using statistics. So a very suitable method for when you compare numeric versus numeric is to maybe you can look at the Pearson correlation. See categorical or numeric versus Pearson correlation is one, ANOVA is other, but you don't have a situation here. If you look at numeric versus possibly categorical, you can look at ANOVA again. You can look at probability, probability information, right? Or maybe the feature information present in that, right? And similarly, categorical versus categorical, you can look at, there are statistical methods like chi-square test, right? Mutual information. Mutual information is also applicable to numeric versus categorical as well, right? So mutual information is also applicable here. These are a lot of methods. We will not cover all these methods. This is just for generic logical understanding, right? But yeah, these are all different methods which exist, when you want to do comparison similarly using statistics, right? When you want to do EDA and you want to see impact of one attribute on the other attribute using statistics. Pearson correlation also works quite it gives you quite good information about when you want to compare numeric versus numeric as well as numeric versus categorical to a large extent. In case categorical is two categories and that's available in the form of numbers. ANOVA works for numeric, yeah. So we have a method in Python where ANOVA works for numeric versus numeric as well. So we're going to be looking at the impact, use of ANOVA here for numeric versus categorical, right? So I'm going to show a sample example of using ANOVA for importance, right? So ANOVA simply, it uses a null hypothesis, right? It uses a simple null hypothesis that the distribution of a numeric attribute is uniform among multiple categories or groups, right? And alternate is just, it is not uniform. You can say alternate hypothesis is not uniform. For a business confidence of, let's say, 95%, we can look at the p-value. So for business confidence equals to 95%, which is like 0.95, you can say significance level could be 5%. Maybe some of you who are not from statistics background, this might look a little complex to interpret, so don't worry about that. As this is a workshop, we cannot kind of dive deeper into this, but in general trainings at Tectonic Ventures, we kind of go pretty much deeper into these concepts and discuss them in very much detail to understand them. So yeah, if there's a situation, generally you can look at a p-value, right? So if p-value is, let's say it's greater than or equal to 0.05, it's greater than or equal to 0.05, we say that null hypothesis is rejected and the feature is important. If p-value is it is less than 0.05, my bad. If p-value is less than 0.05, we say null hypothesis is rejected and feature is important. If it is greater than 0.05, we say that null hypothesis is accepted and the feature is not important, right? So we can do the similar analytics with the help of this as well, right? So let me show you an example. Right. So for this, we can simply say from sklearn dot feature selection import f classic, right? As we are dealing with categorical. We can simply say that all the numerics, right? We can simply say all the numerics, which is like we already have numeric columns, right? So for all, or we can say that d of num equals to df of numerics, and we can simply apply. We can say f underscore classic df num comma df dot broken, and it actually is, so you can say which is the p-value. I'm just missing the order of it. Hold on for a moment. Yeah. So first is f statistics. I think, yeah. So f value comma p value equal to this, and maybe you don't want to print it. So let's say for call in numeric, print the call, comma, or for I in range of length of numeric, print numeric of I, comma, p value of I. It should be p value here. So we got p value for lifetime pressure, moisture, and temperature, and we can see that this is 2.3 into 10 to the power minus 149. 10 to the power minus 149, which is like lesser than 0.05, right? So you can say that for lifetime, the p value is lesser than 0.05. So null hypothesis is rejected, and the feature is important feature. Whereas for pressure, as you can see that for pressure, the p value is higher than 0.05. Null hypothesis is accepted and the feature is not important. We also seen that in bivariate analysis as well with data visualization. Moisture 3.4 into E minus 66. E minus 66 means 10 to the power minus 66. So that is lesser than 0.05. So the feature hypothesis null is rejected and the feature is important. Temperature 0.73, right? So it is higher than 0.05. Null hypothesis is accepted and the feature is not important. So the same analysis which we have seen earlier with the graphical visualization, we can also see that with the statistics as well, right? So statistics and data visualization are two different ways to do EDA. It just data visualization shows you whether it is important or not important. It also shows you why and how it is important, but statistics doesn't show you why and how. For example, statistics simply shows that moisture is an important factor, but it doesn't show that more than 120 moisture, almost all the machines are getting damaged. Statistics shows that lifetime is important, but it doesn't show that the machines which are having lifetime more than 60 months are getting damaged because they are older, they are getting damaged. So it doesn't show why it is important or how it is impacting or how it is important. It simply shows whether it is yes or no, like that. So that's why data visualization is super important in the EDA spectrum, or you can say EDA process. So otherwise, one such method, there are similarly other methods like, each method doesn't have p-value. For example, p-value is there with ANOVA, chi-square test also has a p-value. Pearson has correlation, correlation values which is between -1 to +1. Mutual information has different other values between 0 to 1 or like that. So these are different values that we sort of make sense of, and we interpret whether the feature is important or not. Right. So that's the idea, everyone. That's the idea about it. I hope we're good. Any question we have, let me know. Are we all good? Okay. So finally, you can say the report part, which could be, so we may want to write some red alerts, right? So let's say possibly, possibly you may want to write some red alerts, which could be machines having age higher than 60 months are damaged. Machines being operated or machines generating moisture more than 130 are getting damaged, possibly, right? So that's what, if I'm not wrong with the figure. We can simply say that, few noteworthy points, right? So few points to consider. Machines, you can say machines produced by provider 3 are least qualitative, provider 2 are most qualitative, right? So machines provided by provider 2 are most qualitative. And are surviving longer, whereas machines provided by provider 3 are damaged early. Right, so these are some few noteworthy points. There could be even more as we explore. We can add those over here and finally create a report on the top of this. Right, so that's the sort of nutshell idea about it. Right, so that was the nutshell idea about this data analytics project. So yes, with that part, we are done with this part now, and we are open to questions. We'll be dedicating next 5 minutes for question, and then we have few set of offerings to show, right, which you must be interested into to learn further about this, right? So yeah, we are open for questions, everyone. All right. So we're good so far, right? I would encourage you all to look at our YouTube channel, right? So we have similar more videos and of the workshops taken earlier. We have even more workshops coming up. We might have in next few months. So every month we kind of organize around 1 or 2 workshops similar to this. I'm not sure if there is any certification associated with this because we mostly organize this for the knowledge perspective rather than giving certificates, right? So you may not get a certificate for this workshop. This was more for knowledge perspective, right? So there's no certificate associated with this workshop. So please, if you have any question about certificate, right? So there's a clear answer. There's no certificate associated with this workshop. This is more for learning perspective, right? So because providing certificates adds a logistic cost to us, which stops us from organizing such workshops, because there's a huge cost associated with certificate of providing and writing names and all. So yeah, that's one of the point. And the today's recorded lecture will be available on YouTube, as you would have already received the link for the yesterday's video, which is already uploaded on YouTube. I would encourage you all to check our channel for more videos and for this video as well. You can already find the yesterday's video on the YouTube channel of Technical Ventures. There's a question, as a fresher, how much amount of data analytics should one know? Well, there's no limit, right? Even people who are freshers, they are into first or second year, they are pretty good data analysts as well, right? So there's no limit of how much you should know, but you should kind of, if you have interest in this, you should definitely work on this and explore more, practice a lot, right? At least you should know a good amount of statistics, I would say. And the few skills that in order to get absorbed as a fresher include good foundation on statistics, good foundation on SQL, right? So SQL basics and all, good foundation on few of the other tools, which could be possibly Tableau or even few other tools, which could be basic Python, which is like pandas, NumPy, Matplotlib, Seaborn, or few of the other tools which are important, I think. Yeah, based on my understanding and experience. There's a question which is like, it is important to do both visualization and statistics in EDA. Visualization is super important. Visualization gives you more curiosity, understanding about what is happening, why is it happening. Statistics confirms those findings. So visualization helps you to create some doubts and some logics, and you verify them by statistics. So both are important, yes. There's a question on fourth engineering, and as a fresher, how much? Yeah, so I have answered that question. There's a question. Yeah, thank you, Mr. Ramchandra. All right. So are we all good, everyone? Any more questions? So I'm gonna hand over this to one of the executive at our company, who is Sagir. So he's going to be taking you through a few other offerings that we have, and the kind of courses that we generally organize, which cover many of these stuff, and which is like super interesting thing. I hope you must be looking for something similar to that, right? So now I'm going to be handing this to Sagir. So yeah, Sagir, are you there?
Yeah, Ansu, I'm here only.
All right. So what do you?
Yeah, Ansu, thank you, Ansu. Can you enable me for screen sharing, Ansu?